What if the future of quantum computing hinged on something as small as a single photon? Today I'm joined by the CEO of MicroAlign, and together we're going to discuss the cutting-edge innovations that are solving some of the biggest challenges in quantum photonics: efficient fibre-to-chip connections. And MicroAlign's technology was born out of a PhD project at Eindhoven University of Technology, but it's now revolutionizing how photons are transmitted between components in quantum computers. And with quantum computing requiring extreme precision, something where every photon counts, MicroAlign's next-generation fibre array technology is attempting to offer seamless, high-efficiency connections that could help scale quantum systems to millions of qubits. But the impact of this breakthrough goes beyond quantum computing. I want to explore data centers, AI, telecom, and even space communication, how all these areas could benefit from this advancement in fibre alignment. So my guest today will break down MicroAlign's nanometer precision fibre alignment technology, talk about how it works, the challenges of scaling production, and what the future holds for photonic computing and beyond. Could this be the missing piece that accelerates the next era of computing? Let's find out by getting today's guest onto the podcast. So thank you for joining me on the podcast today. Can you tell everyone listening a little about who you are and what you do?
Sure. Well, thanks, Neil, for having me. I'm Simone Cardarelli, Italian. I'm 34 years old, and I come from this beautiful region called Abruzzo, in the middle of Italy. I have a technical background. I had my bachelor and master degrees in Italy in electrical engineering. I came to the Netherlands in Eindhoven in 2014 for the Erasmus program. That's also where I had my thesis project in optical communication. That's where optical communication or optics entered a bit my life. And then I liked it so much to stay in the Netherlands, I decided also to stay for my PhD project, which then connects to the whole rest of my life. I finished my PhD in 2019. In 2021, I co-founded MicroAlign, and now I currently work as CEO at MicroAlign, where we develop solutions for efficient optical fiber connectivity. That's a short summary, let's say.
Absolutely love that. There's so much going on with your story. I was doing a little research before you came on the podcast. You just mentioned now going from Italy, beautiful sunshine, beautiful food, to the Netherlands, another beautiful country. And MicroAlign's technology stems from a PhD project that has roots in the Memphis 2 program. So can you tell me a little bit more about that journey from those research days to creating a commercial solution for efficient fiber to photonic chip connections? Feels like there's a big story there.
There is a huge story. It's very exciting. In 2015, there was this project available for PhDs in Eindhoven. It was a project from the Memphis 2 program. The Memphis 2 program was is a program which was founded by the NWO, the Dutch Research Council. And it was about developing different types of technologies for photonics to advance in the photonics industries. That project for myself, well, that PhD that you talk about was my PhD, and it was about connecting optical fiber and photonic chips. So straightforward, very close to the topic of MicroAlign. It was an exciting project that basically was about moving optical beams from photonic chips. So it was like physical movement of optical beams to match optical fibers. So you can get basically all the light from the chips into the fibers so that you can improve the energy efficiency of this transmission and the performance of different chips. That was the idea. It was like a waterfall of new knowledge that I had to get from photonic chips, everything. It was ups and downs, very frustrating, right? Because in this PhD, it was included a lot of physical fabrication of photonic chips. And we explored like so many ways of performing this connection in a better way. And I need to say that actually one of the last ideas that we came out with was about, okay, but why don't we make the possibility of getting a more efficient connection, not in the photonic chip, which was anyway a brilliant idea, but off the photonic chip? Can we make like some kind of mechanical chip that can actually move the optical fibers and connect them better, in a better way to a photonic chip? That was kind of the spark that there was at the end of my PhD. But we saw so much potential basically in this spark that we totally pursued it as an option, as a solution. The funny part is basically that I didn't do, of course, as everything, all of this myself. It was cool that basically at the same period, and that's the funny part of the story, there was a good friend of mine, also Italian, that came together with me from Italy for the Erasmus. He also had the PhD at the same university, and together basically we worked at the feasibility of this solution, right? So we kind of did all the steps together from bachelor, master, PhD in the same university, and then I asked this guy, Marco, which now is the CTO of the company, Marco, why don't we basically demonstrate this solution as technology? And then basically he thought, wow, this is very exciting. He's an electronics guy. I was a photonics guy. And then in the research group, there was also this suggestion, okay, guys, now we developed this nice technology. Why don't we make a company out of it? Because, of course, the Eindhoven University of Technology was very well connected to the industry around. Eindhoven is a nice hub, photonics. And that's where basically all the pieces came together, the proof of the technology, the possibility of exploiting commercially, the connection to the industry. And basically we decided, okay, here there is something that we can dive into. And I was excited about this journey. It was a bit difficult to decide, okay, now I'm going to switch from a research and academic career to an entrepreneurial career. But I had, let's say, good advisors close to me that could guide me in the right direction without having the feeling of missing out here or there. That's how it went, basically.
Well, an incredibly cool story. For non-techies listening, got business leaders listening around the world, all I will say is in quantum computing, every photon counts. So the question I have to ask you is, how do you address this challenge, especially with MicroAlign's next generation fiber array technology? And my understanding is that you are able to optimize photon transmission. So can you tell me a little bit more about that and how it ultimately enables a more efficient quantum computing?
So basically, when we talk about computing in this sense, well, as there are many technologies to make a quantum computer, in MicroAlign, we focus on technologies based on photonic chips. So quantum computing that happens by using chips that work with light. And there are several parts of a quantum computer based on photonics, going from sources of photons, processors of photons, and detectors of photons. And all of these parts in a quantum computer, they have to work together. And as there is a lot of also hype in saying that a practical computer needs to have like millions of qubits, and qubits basically translate in photons, you can imagine that a quantum computer will have like hundreds of optical chips connected to hundreds or thousands of optical fibers. And as a photon cannot be split, basically, it can just go through this system or not through, right? The photon has to be generated, processed, and then detected. And many of them, they have to go through this process in parallel. Well, basically, one of them is lost. Information is lost. Computation has to be done again. So basically, each photon that gets lost through the way is a problem in terms of computation performance. A photon is a very small quantity of energy, and if only 1 out of 100 times it gets lost, only one photon for one fiber, you can imagine that for thousands of fibers, it's very easy that somewhere these photons get lost. So that's where we come in this basically super tight photon transmission request, where basically we make perfect fiber arrays. Fiber arrays are fiber connectors that you can plug to a photonic chip, and you make sure that in this fiber connector there are like 20, 30, or 100 fibers, where all the fibers are very well aligned. They perfectly match the let's say the input-output ports of the chips, and you make sure that the photons get lost as little as possible in this connection. That's basically how we help and we enable photon transmission by having this high accuracy fiber array.
And before you came on the podcast, I was reading that you've recently developed your first prototypes and are planning to scale production. So again, what challenges and opportunities do you foresee, especially as we move towards this large scale manufacturing and bringing everything to life that we're talking about today? What's happening here? What challenges and opportunities are you experiencing?
Yeah. In terms of, well, let's say the challenges, if we want to define them as problems along the way, and the way we take this path because of the opportunity here is indeed is that we can help not only in quantum computing, but also, let's say, more applications, right? Going from datacom, telecom. And the opportunity is that we can redefine basically a standard for the fiber connectivity. We can make the base fiber connectors, we can improve the energy efficiency as much as possible in the connection between fibers and chips. This is the opportunity where actually we can bring in terms of solution, and then with all the consequences that it has for the different markets, including the quantum computing. All of these markets, well, or many of them, they require indeed scalability in terms of production. And we are talking about hundreds of thousands of samples of connectors per year. If we look at datacom or telecom, it's also millions. And this requires certain level of automation. And here is basically where the challenges come. When it's about automation of optical components based on fibers, this is kind of a hell of a job. And it's not, let's say, for the high accuracy alignment core technology that we have, but it's everything around actually the handy part, the manual part, handling fibers, bringing a wire of glass from one machine to another, hundreds of thousands of times per year with high yield. So basically that's where the challenge is automation of a process in a way that is reliable and handling glass material without breaking it. And if we manage, let's say, to achieve this type of, let's say, manufacturing method where we can have at the same time high automation and high accuracy, well, then again, the opportunity is that this will be very appealing for a set of applications, not only for quantum.
Fantastic. And if we were to dare to look even beyond quantum photonic computers or just differently and bigger, I mean, how do you envision MicroAlign's technology to being applied in other areas? I mean, you mentioned datacom there, but also things like space communication, AI, sensing. It feels like there's a long list of other uses there too.
Yes, absolutely. Well, let's say that as a good practice for customer interviewing phase of a startup, we started like 3-4 years ago, right after the COVID, a customer interview phase in a more intense way, what we called customer discovery, right? And we started to have discussions and conversations with a bunch of, with a lot of companies in different domains. There was so we could talk about datacom domain, telecom domain, of course, also quantum domain. And at that point, 3 years ago, we realized that the key, let's say the killer application was quantum computing. And we thought, okay, there was also interesting different domain, but it was not like as much as in quantum. Along the years, we realized that there was a trend in concerns of energy efficiency, which was much, much more tight than we saw 3 years ago. And not only for communication applications, but also for new applications like sensing or virtual reality. And we realized that, okay, it's happening now, something that there are so many new photonic chips that companies are producing, developing, that actually require new functionalities, more optical fibers. And that's where basically this high-end or killing application in quantum now is also getting close to other applications where, for example, visible light is used. This is a specific example where photonic chips work with visible light, red, green, and blue, for example. And with visible light, the optical beams are even more difficult to be aligned to photonic fibers, to optical fibers. So that's one case. If we look at how much AI is consuming in terms of data computing, in 3-4 years from now, there is a shift of paradigm in data centers going on. That's called co-packaged optics, where basically all the transceivers will be encapsulated in one package, and there will be many fibers in those packages. And these many fibers have to be aligned with high accuracy because by that time, looks like that the forecast is that 1 to 3% of energy connection between the fiber and the chip also will be important. So that's basically how it happened. We started from a field where we clearly identified the let's say the beachhead market, quantum computing, and looks like that everyone is kind of aligning in different levels to that type of requests for either now or let's say for future applications.
And one of the big things I've learned in 10 years of doing this podcast is efficient fiber to chip coupling has often been seen as the big bottleneck in photonics. How does your solution differ from those traditional approaches, and what impact could this have on the broader photonics industry, just for people listening outside of the industry to understand the magnitude of what we're talking about here?
Current methods basically to produce the same component that now we are developing are basically based almost on a manual procedure. So the current methods to make these fiber connectors is called V-groove based. Simply speaking, now you can, in order to make this connector, you can basically push optical fiber with your thumb on a substrate that is engraved with V-grooves. These V-grooves have the shape of a V. They are parallel lanes. You push the fibers in, and then you cup them with a lid, you press them, you glue everything together, and you end up with a fiber array where there are parallel fibers in a glass block, basically. This method is called the passive alignment because there is no control on the fiber position. The fibers are just reaching the final positioning in this V shape of the groove, and that's it. There are a number of imperfections that basically are a problem with this procedure, going from all the fibers are not exactly the same. The part where the light comes from the fibers, what we call core, is not exactly in the middle of the fibers. The diameter is not the same. And when you glue them and the glue becomes hard, they move a bit. So there are all of these imperfections that are not taken under control during this process. And that's basically what limits the performance of the precision of the alignment of these fibers in these fiber arrays to, let's say, plus minus half a micron. So we need to see it like, okay, each fiber is in its position with an offset from the ideal target, which is basically a total of 1 micron around the ideal position. The way we are different is basically that with this micro-actuator, it's a small robot that we developed during my PhD. We can control the position of each fiber. So up to a level of 100 nanometers. So 10 times less than 1 micron. So basically you end up with our connector where each fiber is accurately positioned. The good thing is that if you go to 10, 20, 30 fibers, as we have independent control on each fiber, this technology has high potential for scalability because the performance is not expected to degrade with many optical fibers in the connector. While for current technologies, the error or the imperfections in the connector grow up when you add more fibers to the game.
And as quantum computing continues to evolve and we all begin exploring the art of the possible and what this technology could mean in real terms, in business terms, how do you see MicroAlign's role in helping shaping that future in this emerging field?
I see MicroAlign as a player that supports these companies, this field, the development of this field in a bottleneck problem, which is connection of efficient transmission of photons. What we can do is basically to improve the performance of that these companies are now producing, which are, for example, computers for prototyping activities or for R&D, but also basically we can improve and we can make sure that in the future where many photonic chips will be used in the computers, actually we can connect them efficiently. So imagine that company developing quantum photonic computers have like hundreds of challenges they are working on at the same time, going from electronics challenge, photonics challenge, mechanical challenge, packaging challenges. And for each of these challenges, they need to achieve the highest, basically, performance. So state-of-art performance for every type of part of the system that they need to use. In our case, basically, when it's about fiber connection, this is also a huge topic, a bottleneck. And basically, this knob they don't have to work so much on it, because basically the companies make computers, they can be sure, or they can rely on us to develop a solution for them. So that's how we see that we can help shape this future. We can basically help them to speed up also the adoption of computers, because they have one important problem less to think about.
And I suspect for many people listening, they're just wrapping their heads around this technology and what it could mean. But as someone right in the heart of this space, if we look ahead, what particular advancements or maybe even innovations excite you the most, especially around photonics and quantum computing? And how do you see MicroAlign preparing to contribute to some of those developments too? Or should I just say, what makes you want to jump out of bed in the morning with this?
That's a great question. And I think that indeed, thinking about quantum photonic computing at the moment is like the technology that we think the most of, that it really triggers also our days, that gives us energy, right, to jump on that train. Because the way I see it is that basically, when I look at the promises and the opportunities that this technology, the quantum computing gives to the society, going from molecular engineering to cure diseases, right? Or weather forecast, or whatever it helps, drug analysis. I was hearing just a few days ago, and now it's a bit between the scientific opportunity and a bit the magic, right? Or what we consider magic as thing that we didn't understand yet. But there was this quantum scientist saying that basically quantum computers in the future may also help to stop aging, right? Aging. So this is kind of the things that you say, okay, this sounds like a bit over optimistic, but he gives a logic explanation, right? And it gives an idea of what is the potential behind that maybe that for sure we didn't exploit yet. So looking at this train called quantum computing that is going in that direction where nobody went before, that can help the society to make leaps in different domains of thousands of years, that's kind of the train that you want to be in, the train that we jumped in. In general, let's say, also getting from far or expanding a bit more, looks like that telecom technologies are being, let's say, developed with all sorts of photonic chips that have like 1,000 functions now, right? There's not only a laser like in the past. Now photonic chips are becoming photonic integrated circuits. So photonic chips, they implement circuits with different functions, laser, amplifiers, filters. All of these innovations are quite exciting because basically open all sorts of opportunities to have energy efficiency functions. It can be, for example, writing with a laser beam a message on your glass, right? And that becomes, let's say, augmented reality. That's also quite exciting. And that's all the way I see it, that it looks like that all of these photonic applications where fibers can get connected, it feels like we can be needed there in the future, right? So that's also, I'm excited to see what happens in the future, because fibers are everywhere somehow when it's about optical components.
Well, I've enjoyed geeking out with you today. So thank you so much for sharing your insights around photonics and quantum computing. But before I let you go, I'm going to ask you to leave one final gift for everyone listening. It's time to have a bit of fun with you. I've got a Spotify playlist where guests add songs to that playlist, and an Amazon wish list where guests can add books. All I'm going to ask is, what would you like to leave everyone listening, and why?
I would like to leave actually a song.
Yes.
The song is called Born to be Wild from Steppenwolf. The reason for this is that Born to be Wild was a bit our company song in 2024, last year. We had this huge, let's say, business model change, right? Which, this is the interesting part of the story, that went from selling our micro robot that aligns the fibers to actually making the fiber connectors. And when we discussed it internally and externally, right, this plan with our shareholders and stakeholders, everyone was like, wow, this is a wild plan. Do you think you can actually make it? And we squeezed all the energies basically in our company, positive energies, because everyone was very excited to perform on this plan, to achieve the milestones. And one of the songs, so basically indeed, that we used to load ourselves with energy was this one, Born to be Wild. And the idea of this song came over from Mr. Ruton, one of our advisors, that said, "Wow, guys, you're very crazy to do this in such a short time." And that's why I want to give this song also as an inspiration for all, I think, of the startups that want to rock and squeeze years of development in a few months.
Wow, absolutely great story behind it, and a killer tune as well. And I think I must have some kind of musical Tourette's, because all I can hear in my head right now is "Get Your Motor Running," cracking intro. So I will get that straight added to the Spotify playlist. And for anyone listening wanting to find out more information about the great work you're doing with MicroAlign and maybe carry on the conversation, where would you like to point them to now?
Yeah, sure. I would welcome everyone to visit, first of all, our website, microalign.nl. That's basically they can have access to our contact information, to our news, to our technology description, and to read more about us. And also, of course, for sure, they can visit us on our LinkedIn page. So both of them are great.
Well, again, can't thank you enough for coming on today, learning more about how you're enabling efficient optical connection in quantum photonic computers, and how the solution consists of this new generation of fiber arrays, which ultimately enable efficient fiber to photonic chip connection. We could have talked about this for hours, but just a big thank you for starting the conversation and bringing it all to life today. Thanks for joining me.
Yeah, thank you very much, Nate, for this opportunity of sharing about us.
I think the future of quantum computing and many other high-performance technologies all depend on solving the problem of efficient light transmission. From photon loss minimization to nanometer precise fiber alignment, MicroAlign's innovations could redefine how we connect and scale quantum photonics, and in doing so, unlock new possibilities in everything from AI, telecom, and even space communication. But as we've heard today, technological breakthroughs aren't just about discovery. They require scaling, precision engineering, and the right infrastructure to reach their full potential. So the question is now, are we ready to rethink connectivity at the microscopic level and unlock the macroscopic future of computing? Love to hear your thoughts on the impact of quantum photonics and the role of fiber optic innovations. What role do you see this playing in the next generation of technology? Email me, techblogwriter@outlook.com, LinkedIn, X, Instagram, just @Neil C. Hughes. Love to hear your thoughts on this one. But until next time, stay curious, keep exploring the cutting edges of technology, and join me again tomorrow where I've got another guest lined up for your listening pleasure. Let's see what we can learn together. But that's it for today, so speak with you all bright and early tomorrow. Bye for now.